Hello, my name is Randy Lemons, and I want to talk to you about the next generation of photoinjectors for linear accelerators and X-ray free electron lasers. Photoinjectors are the first electron beam component in ultra-short electron guns and XFELs. Electron beam parameters are largely set in these devices as the intrabeam dynamics due to Coulombic repulsion are not yet damped by relativistic speeds. Currently, photoinjectors around the world not dedicated to photoinjector improvement research make use of outdated and simple laser systems that are ultimately suboptimal to electron beam generation. Due to the importance of the photoinjector, the overall performance of the instruments is also decreased due to these effects. Naturally, coming from SLAC, we are focused on the effect of the photoinjector on the X-ray free electron laser. In particular today, the one resulting from the LCLS2 accelerator. This accelerator is designed to operate at a much higher repetition rate and energy than LCLS1 and above other XFELs around the world. However, in order to extend these goals to meet highly desired operational energies, there needs to be a significant reduction in the emittance off the photocathode for the electrons to reach these new energies. As such, there's two main challenges that face the current state of photocathode technology. The first is a broad reduction in electron beam emittance, what I'll be focusing on today, and the other is scaling these ideas to extreme UV powers. In any photocathode system, there's the fundamental issue of shaping the temporal profile of the excitation light, as Gaussian pulses do not result in the best electron performance. For ideal performance, the incident light should be in the deep UV and flat top in time with sharp rise and fall times, and be on the order of tens of picoseconds. The lasers that back these systems have natural pulse durations on the order of hundreds of femtoseconds and commonly in the near IR. As such, the first step is to convert to the UV. To create a long flat top pulse from this, the common method is to coherently stack multiple copies of the initial pulse in time. This method, called pulse stacking, utilizes the splitting and delay of optical signals when traveling through birefringent materials. To get a coherent signal, one must also use a polarizer to cut out at least 50% of the optical power in order to realign the delayed pulses along the same polarization. The resulting combination from these devices, however, is far from ideal, displaying large intensity modulations on the picosecond scale, which has been shown to increase emittance. It is non-flat spectral phase and varying amplitude that leads to the peaked nature of the pulse stacker pulses. So the challenge at hand is converting femtosecond pulses to picosecond pulses while giving them a flat top shape to reach this emittance reducing profile. Ideally, in a process that combines all of these steps. I want to take a quick detour to a background topic that I hope will aid in the understanding of our methods, and that's the mathematical description of the electric field of laser pulse, in particular, a description of the previously mentioned spectral phase. The pulse is given by an amplitude function and a phase function. The spectral phase determines the position in time of each frequency, and in a broadband pulse, its temporal shape. The phase is described as a Taylor expansion around the central frequency of the pulse. And the first terms in this correspond to the position of the carrier envelope, or the carrier with respect to the envelope, known as the carrier envelope phase, and the shift in time from a fixed point. For our purposes, these two are negligible and arbitrary respectively. The next term, SOD, second order dispersion, is where the instantaneous frequency of the pulse depends linearly on time, and for Gaussian pulses manifests as a symmetric elongation. With the last term considered today, third order dispersion, TOD, the instantaneous frequency is now dependent on the quadratic function and results in the temporal envelope developing pre or post pulses depending on the sign of TOD. It is these terms, second order and third order, that we are interested in. So back to our challenge. To generate picosecond pulses from femtosecond pulses, there's an old technique where the original femtosecond pulse is split and an equal and opposite amount of second order dispersion is added to each copy. When these femtosecond pulses that have been given a linear ramp and stretched to picoseconds are temporally overlapped and non-linearly combined in a nonlinear conversion crystal, the dominant conversion process is SFG. This is because at any point in time, the overlap frequencies are the ones which are equal distant from the central frequency. As a result, the combined pulse is not only of similar time duration, but also has a drastically narrowed spectrum to the point of being near transform limited. However, this pulse is still only in an elongated Gaussian shape and does not resemble the ideal flat top that we're searching for. So we add third order dispersion to the mix. These are the input pulses for non-collinear SFG that I was just showing, with varying amounts of second order and third order dispersion. The blue pulses have negative SOD and positive TOD, and the red pulses have positive SOD and negative TOD. The most prominent features here are that SOD dominantly controls the pulse duration, while TOD controls the sharpness of the rising or falling sides. However, it's still unclear a priori how the magnitude of each will affect the pulse shape. This is best seen in the middle column, where we have very different pulse shapes for different combinations. So instead, if we define a ratio between TOD and SOD, alpha, displaying pulses now as a combination of SOD and alpha, is clear to see that the pulse shape is based on the singular parameter here, and SOD actually controls pulse duration. The actual magnitude of SOD and TOD in particular on display here are quite large for the common pulses that will be found in photoinjectors. But to achieve these magnitudes, it's sufficient to use a matched compressor stretcher set with an off-litro instance. Moving forward, we're going to focus on pulses in the center column shape with alpha of 0.0125. To evaluate the expected shape of these pulses through the opposite chirped nonlinear conversion scheme, we implemented a symmetrized split-step Fourier modeling method with a fourth-order Runge-Kutta method to handle the nonlinear conversion process. The result is on the right, and to be quite honest, is a fairly ugly pulse. It has ringing that is on the picosecond scale, like with pulse stacking, and a large amplitude fluctuation. However, one interesting and redeeming quality is that the ringing is symmetric and it's focused on the edges of the pulse. This shape is reminiscent of the ringing that shows up with the Gibbs phenomenon. And indeed, we actually see that the spectrum has a long tail of higher and higher frequencies that are contributing to the pulse shape. And by applying a wide spectral filter to dampen these, but not the main lobe, we can improve the pulse shape drastically, all with only a 5% reduction in the overall power. With this addition, we're left with a 20 picosecond pulse demonstrating the sharp rise and fall times, along with a flattened profile from Gaussian. Additionally, due to the opposite chirp conversion process, this pulse has a vastly flattened spectral phase compared to the inputs and is sufficient for direct use in a second harmonic generation stage in order to convert to the UV. Here we're displaying the main elements in the nonlinear conversion chain, including a spectral filter between the first and the second crystals. By adding control of the third order dispersion, which is a realistically achievable assumption, to the non-collinear opposite chirp mixing, we can now generate pulses that on paper should improve electron emittance from photocathodes. In order to evaluate our pulses and their performance, we simulate the photoinjector at LCLS2 and the first few meters of acceleration. This physical simulation includes the photoexcitation dynamics, internal electron gun acceleration, intra-beam space charge forces, and linear acceleration. And additionally, a genetic algorithm was added to optimize the second order and alpha parameters of the laser pulses for any given filter width, all under the current operational machine configurations. The result is that the DC&S pulses improve performance from the Gaussian pulses in use worldwide and reduce electron emittance from the photoinjector at all electron pulse lengths. The graph here displays the points which are at a minimum for any given length or emittance, also known as Pareto optimal. Here we're showing all of the solutions instead of only the Pareto optimal in order to demonstrate the larger space of emittance bunch length combinations that the DC&S pulses enable. To first order, the 25% reduction in emittance corresponds to a 2 times increase in electron beam brightness. And for XFELs, this would mean a 25% shorter achievable X-ray wavelength and a reduction in undulator lengths by 25% as well. Though we're focused on XFELs at SLAC, this technique and improvement are independent of our large machine and remain applicable to all RF photoinjectors and the related technologies that are dependent on them. As a quick comparison with currently implemented beams, the DCNS pulses, by combining shaping and nonlinear conversion, results in nearly an order of magnitude more available photon energy for electron generation at a reduced emittance. We've demonstrated a method to combine UV generation and shaping for the improvement of photoinjectors. Our method incorporates tunable duration and shape and combines shaping with nonlinear conversion. The emittance reduction available would greatly open up the available science at XFEL's facilities and would improve instruments based on these photoinjector devices. Thank you.